Hello everyone, so welcome to the session. So in this session, we'll be discussing a quick revision of microprocessors. Like for your GENCO examination, whatever the required revision that will be done in this particular session. Hardly maybe 2-3 hours. I may take it in a single session. Otherwise, we can make it into parts also. So those who have already studied the microprocessors, for them, this session will be helpful like a quick revision, like it will be helping you like to understand or to recollect all the facts you need to remember for the microprocessor. Other than that, those who are have not prepared this subject, who has left this subject, for them up to some extent this will help you to crack the exam. I'm not saying that within 3 hours you can learn the microprocessor even you don't know anything. That is the fact. If you already have the knowledge, this will definitely help you to revise quickly. If you don't have knowledge also, whatever I can do in this time, in the best possible way, I'll keep all the points in the lowest possible time. And one more thing here, so exam point of view, whatever required, all the points we'll be discussing. So coming to the lecture here, we'll be discussing first with the theory. So I'll just quickly recollect or recover what the necessary theory required for you for the microprocess. Then we'll start the problem. So we'll discuss different topics, 30 questions, and I'll finish it off. So let's start here. So before going for the microprocessor, the first thing we should understand is most of the questions will appear from 8085. Few more questions may be appearing from 8086. Few might come from microcontrollers also, but they will be very basic level questions. So they might be asking you the questions from the microcontroller or 8085. They are very basic level questions, like maybe the properties or the features of 8086. Few questions hardly may come from its instruction set and all. So my suggestion, just before the examination, already because your preparation is done by this time, so my suggestion is read 8085 properly. Over you go with the 8086 and 8051 microcontrollers. So coming to the 8085, here we need to first understand the architecture of 8085. So in this, let's start with the architecture of the 8085. So if you discuss the 8085 architecture, you can see here the first thing which is very important here is the register set of 8085. Here you have some 8-bit registers like temporary registers, general purpose registers, and special purpose registers. So those who don't have any basic idea about microprocessors, for them if you see this figure, it might be very difficult to understand. So for those people, let me start with very basic. So for the computer, what is basically a microprocessor? It is nothing but a computer simply, the input devices, the output devices. Computer will be containing what? Input devices, output devices, and one central processing unit. So that central processing unit, if you embed on a single chip, then it is called as microprocessor. So in the central processing unit, you will be having control unit, and you will be having the registers, and you will be having the arithmetic and logic unit. So what this control unit's purpose is to generate the necessary control signals such that it will do the necessary job. And the ALU job is to perform the arithmetic and logical operations. And the registers will store your program or results temporarily inside the computer. So in the computer, if you see, when you enter some program, the computer need to understand that program. So it will be, we will be giving the program whether in the higher level language or assembly level language, such that the computer is able to understand. So for that, first it will be converted into its own instruction set format. Then it will be converted into ones and zeros. Once it converts into ones and zeros, then it will be decoded. So how the computer will be taking is, so through the address bus. What is the meaning of bus, sir? Bus is nothing but a group of wires. So through the bus, the computer will load to instruction register. So if you want to say computer to do a particular job, please do add operation, subtract operation, multiply operation. We tell it, we give the computer with the help of instruction. So that instruction will be stored in instruction register. Once it is stored in the instruction register, Then what happens is from the instruction register, the computer will be copying to instruction decoder. It will be copying to instruction decoder. In the instruction decoder, computer will understand what is the job you need to perform, whether you need to perform the addition, subtraction, multiplication, everything computer is able to understand with the help of instruction decoder. Then it will convert into necessary parts. We call it as machine cycles. That job is done by this timing and control unit. Suppose you need to perform addition, then it will generate some signal to the arithmetic and logic circuit to activate the adder. If you want to do subtraction, then it will generate some signal such that subtractor will be activated. So to activate that with the help of ones and zeros, there will be some decoder in the circuit which will read these bits and understand, and accordingly it will do it. So all these operations are to be done on some operands. Suppose you want to do a plus b. Plus is the operand. A and b are called as operands. These plus is called operation and A and B are called operands. A plus B is the operation to be performed on the addition is the operation to be performed on the operands A and B. So those are nothing but here registers. In 8085 microprocessor, there is one register which always store the result of all arithmetic and logical operations is called as a name technically accumulator. Okay. There is another register which will give feed the inputs to the ALU, that is nothing but temporary register. So it will take this data from external or this register set and load it to the ALU. So for all this data communication, what we require is a group of wires. Those wires are called as buses. Because all the devices are using the same group of wires, so everybody need those wires only. So what happens is when we use these wires, first we store it temporarily here and we free these wires. Then other devices will be able to use it. So here in 8085, these or any processor, in fact, we call this group of wires as buses. We have three different type of buses: data bus, address bus, and control bus. We'll discuss one by one all of them. So this is a very brief explanation of your architecture of 8085. In this, now we will discuss one by one the register set of 8085, arithmetic and logical operation, interrupt controller, serial controller, timing and control units. All these five parts, one by one, we will be discussing here. Just a moment. Okay. So let's now continue about the features of 8085. Please understand, it is just like a quick revision. We are not covering each and every minute details here. So like a regular class. In 8085, we have 40 pins. In this 40 pins, 27 pins acts as output pins and 21 pins acts as a input pins. Then immediately you will be getting the doubt, sir, you said 40 pins, but these two are giving me 48, sir. Yes, there are 8 pins which are used for common purpose, like address and data buses are multiplexed. I'll explain that. So it is made with a NMOS technology with a clock frequency of 3 MHz. See, understand here, this is the processor made in 1970s. At that time, 3 MHz itself a great speed. Right now, we are running in gigahertz. Our processor speed is 2 GHz, 3 GHz, like that we will be speaking. That is what we call the processor clock frequency. In 8085, what is the clock frequency? It is a 3 MHz made around 3 micrometer, and it has just 6,500 transistors inside this. Do you need to remember all these things? No. At least clock frequency you need to remember, exam point of view, and this one and these things we should remember. Now power supply is around 5 volts, and now these two are very important. In any processor, the data handling capability will decide the processor, what we call size of the processor. Like if I say 8-bit processor, 16-bit processor, 32-bit processor, what is the meaning of this 8-bit or 32-bit or 16-bit is, suppose address bus is 8 bits, data bus is 8 bits, address bus is 16 bit. So the processor is 8 bit or 16 bit. If I ask you what is the answer is, it is 8-bit processor, because this is a very common question asked in many examinations. So suppose address bus, data bus are given. They ask you, suppose the microprocessor is 8-bit processor. What is the data bus? What is the address bus? Address bus is not having any relation with the microprocessor. So if you say 8-bit processor, what is the meaning of that? Data bus size. Data bus size will tell you the data handling capability of the processor, or how many. Suppose if I say 8-bit processor, what is the meaning of it? How many numbers, how many bits I can add at a time. Suppose if I am able to add two 8-bit numbers at a time, if I am able to add two 16-bit numbers at a time, then it is called as a 16-bit processor. So 8-bit processor is able to add two 8-bit number at a time, or subtract two 8-bit numbers at a time, or its internal registers are all, most of them are 8-bit at a time, 8-bit size. So that is the meaning of the 8-bit processor. So what about the address bus, sir? Address, say firstly you understand what is the bus? A group of lines. So data bus means these are used to carry the data. Address bus means these are used to carry the address. Sir, what is address and data also we don't know, no problem. Suppose there is a memory, like your house is there. In house, whatever the people are there, they are called content of the house. Like in memory, the data will be present, and to point this address is required to come to your house. The same way, address is required to point the memory. So in the memory, each location will be given with one specific address, like you are giving your house numbers, right? So the same way here we will be giving you your address bus. Address bus will specify the address or the location of the particular memory. So in 8085 we have 16-bit address. So it can address how many, it can make how many combinations is 2 power 16. That is give you 65536, or you can say 64k different locations it can address. But each location can have how many bits of data is decided by who? Data bus. So that is given by whom? 8-bit. So I can say 64 kilobytes. So what is the memory handling capability of the 8085 is 64 KB, 64 kilobytes, 64K different locations, and each location it can handle. Handle means it can read or it can write up to how many bits at a time? 8 bits. It can read or write or it can carry how many bits? 8 bits. So 2 to the power of how 16 locations, and each location is 8 bits. Let's move further. So basically the data bus, if you see, I can read or write. So the data bus property is, it is bidirectional in nature. If you go by address bus is unidirectional in nature. In 8085 what happens is, higher order address bus is directly available, but the lower order address bus AD7 to AD0 is given with two parts. 1 minute. It is the commonly used for both address and data. Okay, I'll little explain about this. In 8085, how many pins you are having is 40 pins. In that, 2 pins are required for power supply. 2 pins are required giving clock input. So remaining 36 pins are there. In that 36 pins, if you use 16 pins for address bus, 8 pins for data bus, 24 pins are gone there itself. So the remaining pins we need to adjust for all interrupt operations, every read operation, write operation, IO memory, direct memory access. Like that, for all the operations, you need to use the remaining pins only. So it will not be sufficient. So one intelligent way to avoid this problem is to multiplex both the address and data pins. Why? Because if you want to access any memory, what is the first step is, suppose you want to go to any location. First we will take the address, go there, then enter into the home, then we will speak to the people. The same way, when you want to take, read or write the data into any memory, first we will go to that address location. Then we will take the data. We might be writing or we might be reading. The same way, here you understand, address and data both will not come at the same time. First we may keep the address, second we will be reading the data or we will be writing the data. So we will use the same lines for doing both the jobs. In the 8085 40 pins, 8 pins are common for both the address and data. Sir, how the computer will differentiate with these two pins is by using one signal called address latch enable. It will be like this. There will be some latch like 74LS373, and the latch enable is connected to ALE. Whenever it is 1, the address kept here will come here. Or whenever the remaining time, I will keep the data that will come here. So if you see the total architecture, we can divide this architecture into register set, arithmetic and logic unit, the instruction decoder and machine cycle encoder. So once the instruction is kept, it will convert, it will understand what is the job you need to do. That is the decoding part. See here, if you take any instruction, it contains 4 parts. Fetching, which means the reading the instruction, decoding, which means understanding the instruction, then executing means performing that job, like whichever the job you require, addition, subtraction, multiplication, performing that job, and writing the data back, the result, storing the results. That is called memory write back. So instruction decoder will do this job, that is decoding the instruction. And then machine cycle encoder will convert into necessary machine cycles and perform the job with the help of control unit. And we will study now next interrupt controller, serial IO controller. Serial IO controller job is nothing but to perform the serial communication with the help of the two signals, serial input data and serial output data, SID, SOD. And the very important unit is timing and control unit. This timing and control unit generates the necessary signals to activate a particular device or deactivate a particular device. Because what happens is, suppose you want to perform an addition, which you want to add to registers, say A and B are to be added, then result is to be stored in A. So which device is to be activated at which particular time, which register is to be selected at which particular time, all these is done by whom? Timing and control unit. So all the jobs in 8085 are synchronized with the help of clock. Because suppose you want to meet one person, tomorrow I will be meeting you. Definitely what we ask, at what time? So we are all getting synchronized with the help of our clock. The same way, the timing and control unit will be helping you to generate the necessary control signals to activate the particular device, and all the internal devices of 8085 are synchronized with the help of what? Clock. Right. Let's move further. So the user accessible and user non-accessible are the two ways we can differentiate the registers of 8085. What is the meaning of user accessible, sir? If I am able to write some data or read some data from the register using my program directly, then it is called user accessible. If I am not able to access directly, then it is called user not accessible. I'll show you. For example, your all registers like B, C, D, E, H, L, all these registers are user accessible. SP means stack pointer, program counter, all these are user accessible. But this WZ, the temporary registers are used internally by the computer to store some temporary addresses and all. These are user not accessible. This is also user not accessible. And instruction register also user not accessible. It is internally used by the computer. Then if the register is having a specific purpose, we call that register as special purpose register. Otherwise, what we call it as a general purpose register. So in the general purpose register of 8085, we have B, C, D, E, H and L. All these registers are 8-bit registers, and you can combine them to form a 16-bit register also. And the H and L together are called memory pointer. This is also one of the important objective point. WZ are used for temporary register All these are what we call general purpose registers only, but WZ are not user accessible. Let's move further. So very important register in 8085 is accumulator. It is one of the register in all arithmetic and logical operations. It will always in 8085 in any arithmetic operation like addition, subtraction, any arithmetic operation, increment, decrement, result is always saved in where? Accumulator only. So let me explain you one thing. Suppose you want to do x plus y. Here x and y are operands. Z is also your operand. Plus is your operation. So we are performing this operation on these two and saving the result here. So to do these operations, what we use 8085, whether it might use memory, it might use the registers, it might use the immediate data. So in 8085, what I am saying is the result is always saved in what? Accumulator. In all arithmetic and logical operations, one of the operand is by default accumulator only, and the result is always saved in accumulator only. Let's move. Another important register is the program counter. Don't read that. Let me explain you an example. Suppose my computer need to read a series of instructions which are saved like this. So this is at memory 2000, this is at memory 2001, 2003, 2004. So first the computer will read a byte from here. Then it will move here. It will read a byte from here. It will move here. It will read a byte from here. It will move, read a byte from here. It will move, read a byte from here. So automatically after reading a byte, it will move to the next location. How it happens is with the help of program counter in the 8085. So the program counter will be containing the address of the next instruction or next location to be accessed by the processor. This is one of the most important object to be appeared at least n number of times in n different examinations. So please remember this part. There are some exceptions which I generally discuss in regular class. Here in the revision, I don't want to go into that depth. That is like when the processor will not load the next instruction with the program counter, then PC will be incremented or not. Those things, let's not make the complex. So simplest thing is, whenever the 8085, what is the meaning of program counter? It contains, it is a 16-bit register because address is 16-bit now, because it contains the address of the next location to be accessed by the processor. Okay, it is a 16-bit register, user accessible, special purpose register. It is having one specific purpose to do it. The next important register is a stack pointer. So the stack pointer is a 16-bit register, again user accessible, special purpose. Okay, so don't worry to remember the things, automatically it happens. So because when many facts comes into picture, immediately we will feel you need to remember all these things or not. Once we see the problems and all, automatically you will be able to recollect, don't worry. So stack pointer will be containing the address of the top location of the stack. It is a 16-bit register. So what is stack, sir? So stack is a temporary memory which will be accessed in the form of last input, first output. Whichever you keep it in the last, that will be accessed in the first. So that is what we call the top location. So the top location of 8085 stack memory is in the stack pointer. So next register which is very important is a flag register. If you observe the architecture, the result of ALU affect one register called as flag register. So listen here. For example, in C programming, you want to write a program like this. For I equal to 0, for I equal to initially I equal to 5. When I decrement I, then it becomes 4. When I is not equal to 0, go back and do the process again. I equal to 3, I equal to 1, 2, I equal to 1, I equal to 0, stop. So here I am checking I equal to 0 or not. When it is 0, I'll go to some other location. The same way, when I is positive, do this job. If I equal to positive, do this job. I equal to negative, do this job. Like that, When the result is some particular values, we might be doing something, otherwise we might be doing something. This kind of conditional programming is required. Then we need to save some conditions of your result. Those conditions of the result are saved with the help of flag register. It is very important to remember this format also. In 8085, it is a 8-bit register. It has 5 flag bits. So we call S Jack PCY to remember easily. S Z don't care means unused, AC unused, P unused and CY. Here yes, first bit of the flag register will indicate sign of the result. After arithmetic and logical operation, the first bit is called sign bit of the result. If the result is positive, 0 will be stored. Result is negative, 1 will be stored. And the next bit will indicate whether the result is 0 or non-zero. Like previous example, if the result is 0, this 0 flag will become 1. When you do the addition from lower nibble to higher nibble, if there is a carry, it is indicated in auxiliary carry. Similarly, if the number of ones are even or odd in the result is given by parity, that is indicating even parity. And after the addition, subtraction, whatever may be the arithmetic operation, if there is a carry from the most significant bit, that carry is indicated with the help of carry flag. Here the terminology might be new, flag and all, but the content is same as what you studied in the digital. So let's after the registers, let's have a discussion on interrupt structure of 8085. So before going to this, let me explain you what is the meaning of the interrupt. When you are doing a particular job, if somebody disturb you and you deviate, this is what we call interruption. So let's take one example. When you are preparing for the examination, one of your friend came, then what do? Uh, he asked you some doubt. You will be helping him. Then if after help is completed, you come back and study continuously. The same way, when computer is doing a particular job, suddenly some alarm comes. Suddenly some power supply is gone. Suddenly there is some external request to do a particular job. These are called as interrupts. So when that suddenly some external disturbance occurs to the processor or external request occurs to the processor, it will react in different ways. Suppose one particular friend comes, you always say you are not at home. When one particular friend comes, you immediately go and help him. And one particular friend comes, you decide whether to go or not. Like that, computer will also take the decision depending on the type of request comes into the computer. It will decide whether to respond or not, whether what kind of response it need to give. All these things we classify based on interrupts. Interrupt means what? When a computer is performing a particular operation, externally a device or externally one request comes for the computer to stop the current program and perform some other program, which we call interrupt service routine. So the computer might complete the current instruction and accept this interrupt and go to that service. In that, we have different type of interrupts, vectored and non-vectored. What is the meaning of vector? Direction. So when that interrupt request occurs, the computer will go to which location to perform the program is fixed. It is called as vectored, otherwise non-vectored. Next, if that interrupt occurs, the computer will decide whether to respond or not. Suppose you are speaking to a call, you got another call. You may accept that call or neglect that call. This is what we call masking. That is, if the computer is able to, some interrupt has occurred, it can maskable means it can delay that interrupt. It can respond or it may not respond also. These are called maskable interrupts. There are the cases where uh, you cannot escape. When the interrupt occurs, you should respond compulsory. These are called non-maskable interrupts. What are the non-maskable interrupts, sir? What are the non-maskable interrupts we have is in 8085 there is only one interrupt, that is trap. For example, power supply failure has happened, so immediately the system should react, or some fault has happened, fire alarm rings, computer should immediately respond in that case. It don't have any other option. These are called non-maskable interrupts. So in 8085, we have 5 hardware interrupts. In these 5 hardware interrupts, this is the first priority, this is the least priority. Here trap is the high priority interrupt. This is the only non-maskable interrupt. Very many number of times they have questions based on the trap. Only non-maskable interrupt. It is both level and edge triggered. Means it should edge should happen and it should stay for some time. This is a vectored interrupt. What is the meaning of vectored? Means when that interrupt occurs, computer will know where to go. And this is its vectored address. What is that vectored address is? 4.5 into 8 in hexadecimal. It is the highest priority interrupt in 8085. Some power supply failures, etc. occurs, the computer will be able to, those interrupts will be connected here. The next priority is 7.5, the edge triggered interrupt. Then there will be some flip-flop which will save this edge, and even that edge is removed. I mean, just edge comes and gone also, the interrupt will be responded after some time. It is all other interrupts are maskable. Every interrupt is vectored except last one, which is INTR. When it is non-vectored, what is the meaning? When that interrupt occurs, CPU don't know which particular address it need to go. It is not a fixed address. Then that address is all given by this interrupting device where to go. Sir, how to calculate the vector address is, suppose it is 7.5. 7.5 into 8 is the vector address. 6.5 into 8 is the vector address. 5.5 into 8 is the vector address. Here 4.5 into 8 is the vector address. That's why it is also called as RST 4.5. RST means restart. So this table is very important, guys. Example, you can expect some good number of questions, or if interrupt question comes, mostly from this table it can happen. So this is high priority to least priority. So the next, so please remember this, trap is the highest priority interrupt. It is the vectored interrupt with a vector address of 4.5 into 8. Convert into hexadecimal, it will give you 0024 hexadecimal. Only non-maskable interrupt, it is the highest priority, only non-maskable interrupt in 8085. It is used for critical applications like power failures. So all other pins not important. Another important is HLD, hold and HLDA pins of 8085. These are the pins used for direct memory access. What is the use of direct memory access is when external devices require to transfer some data from one device to another device without CPU intervention, we go for the DMA, which will improve the speed. So external device will send request to the processor. I want to transfer the data from one device to another device. If you give your buses, I will transfer it. The CPU will accept it with the help of a signal called as acknowledgement. That is called hold acknowledgement. Similarly, when interrupt request occurs also, computer will give you acknowledgement with the help of interrupt acknowledgement. So kindly wait for some time. My theory will be completed. Then we will do only questions also. So the instruction in 8085, the total job of the processor is divided into instruction cycle, machine cycle, execute cycle, everything I will explain. So one instruction is the time required to complete the one complete instruction. It contains the job of fetching, decoding, executing, everything. So that further divided into fetch cycle in 8085, which contains the reading the instruction and decoding also. In 8085, fetch and decode together is called fetch. And the next part is executive. It is the time required to execute the instruction, means perform the operation. Suppose it will understand here which operation is to be done. Here it will understand the operation is to be performed. The next important is machine cycle. What is the meaning of machine cycle is each operation requires reading the data, writing the data into the memory, into the IO, different jobs. One simple job is what we call one machine cycle. one machine cycle, how much time is required is measured with the help of number of clock pulses required. And one clock is called 1 T state. One clock time is called 1 T state. That is the technical terminology. In 8085, these are the different machine cycles available. The first one is opcode fetch, which requires 4 T states or 6 T states, depends on the instruction. What is the meaning of opcode fetch is read the instruction from the memory and load it into the instruction register. Read the instruction from the memory and loading into the instruction register, and it will also decode during that period. After that, maybe memory read, memory write means reading the data from the memory or writing the data from the memory requires 3 time clock pulses. IO read, IO write, everything require 3 clock pulses. Interrupt acknowledgement, bus idle means when computer is doing long jobs, then the buses externally they are free. Bus idle means doing nothing. So you can remember these values, maybe exam point of view they will be important. Right. Don't read this much. It will not help you. Just for your understanding, I have kept everything. See here. In 8085, the instruction set contains different type of instructions. One is 1 byte instruction, 2 byte instruction, and 3 byte instruction. 1 byte instruction requires 1 byte of memory, 2 byte instruction requires 2 bytes of memory, and 3 byte instruction requires 3 bytes of memory. In 1 byte instruction, you will be having opcode only. The 2 byte instruction, 1 byte is for opcode, first byte is always opcode. Sir, what is this opcode, sir? Opcode is nothing but operation code, machine code, ones and zeros that will be given to the computer to indicate which job is to be performed. Okay, so that is your first byte. The second byte will be the address or immediate data. Similarly, in 3 byte instruction also, first byte will be the opcodes. The second, third byte might be the 2 byte address or 2 byte data also. So 8085, the instructions, suppose I want to do some operation. I want to do some operation. The operation will be performed on some operands. For example, I want to do add 2 plus 3. 2 plus 3 is to be added and 5 is to be stored. So where is this 2? Where is this 3? They will be in memory. No? From memory, I need to take that 2. From memory, I need to take that 3 and add them and maybe storing back into the memory. Right. So addressing mode is one concept which will specify where is the data and how it is located. In that first, in 8085, we have 5 type of addressing modes. The first one is register addressing mode. The second one is direct addressing mode. The third one, register indirect addressing mode. The fourth one, immediate addressing mode. The fifth one, implicit addressing mode. In the register addressing mode, the data will be present in the register. For example, move A comma B. Here, where I want to copy this data here, this is an example of register addressing mode. Similarly, direct addressing mode. Directly in the instruction, I will specify the address where the data is present. There is another way is called indirect addressing mode. There, I will specify one register. That register will contain the address where the data is present. This is called a pointers concept. Because I want to go to 2000 location. Suppose 1000 bytes are there. I want to copy these 1000 bytes and copy to the next location. So what I will do is I will from 1000 location next to 1001, 1002 like that all locations I need to go. Then first location is copied into some register. Then the register will be incremented. Next location we will go and we will copy the data. This is called register indirect addressing mode. So here where I need to copy the data is at one particular address. That address is in some register. The next one is immediate addressing mode. Here, the data is immediately given in the instruction itself. The last one is implicit. Implicit means hidden. Here, there will not be any specific operand directly specified. Instruction itself will operate on one particular specific operand only. Mostly they will happen only on accumulator. For example, there is one instruction called CMA, complement accumulator. It will not happen on any other register other than accumulator. So in the instruction itself, it is indirectly specified. You can see here. In implied addressing mode, it is hidden. The data to be operated is available in the instruction itself, right? For example, complement accumulator, rotate accumulator, etc. All these are examples of your immediate or implicit or implied addressing mode. All these here where you will be performing the operation is fixed. So that finishes the basic theory of 8085 microprocessor architecture and pin diagram. Now we will discuss the instruction set and we'll solve the problems. Before that, let's see few questions, then again instruction set, then few questions we'll be doing it. Listen here, because up to now whatever we discussed, based on that, let's see few questions. So a microprocessor contains the instruction register of size 32 bits. Okay, so let me do this. I have a microprocessor with instruction set 32 bits. If maybe because of the noise cancellation, audio might be low, you can increase the volume, keep the earphones, or don't run the fan so that you can listen more clearly. It has 50 instructions, 64 address lines. Each instruction contains opcode, 2 register operands, 1 immediate data. Okay. And each instruction is of size 32 bits. Determine the maximum value of immediate data. So it looks complex, but not much difficult. Let me show you. The instruction set size is 32 bit. It has 50 instructions. So opcode will specify which instruction it is. To specify the 50 different instructions, we require how many bits is log to the base 250, approximately 6 bits. How many registers are there? 64 registers. So to identify which particular register I need to do the job, log to the base 264. Excuse me. 6 bits are so 6 bits are required for this. 6 bits are required for this. Because here opcode is to be specified means which job is to be done, 50 jobs. So all zeros to up to some 49, you can say 0 to 49, 50 different codes generated can be required 6 bits here. Here 6 bits required, here 6 bits. So out of the 30 to 18 bits are required to specify these 3. So remaining how many bits are required? 32 minus 18 will give you 14 bits are required. So these 14 bits are used for immediate data. In unsigned magnitude representation, what is the maximum number I can save here is given by the formula 2 to the power of 14 minus 1. That will give you 1638. You have 32 bits. In that 3 specifiers, each specifier requires 6 bits. How I decided that? Log to the base to this. And the remaining 14 bits are there. In that 14 bits, what is the maximum number I can write is the question. Okay, clear? So let's move for the next. So this is the first question on this. So the register which keeps the track of the sequence of the instruction execution. What is that in register? Just now we have discussed in the theory. Program counter, right? Next question. So consider the statements regarding the reset instruction. Actually, this one is not done. Okay. Which of the following registers, 8-bit registers of 8085 can be paired together? I told you B and C, D, E, HL are the register pairs. So BC can be clubbed, DE can be clubbed, H and L can be clubbed. So 2, 3, 4 is the right answer. The address bus of 8085 is 16 bits. Hence the memory which can be accessed by this. So what I told, to the power of 16. How much it is? 64 KB. So here let's have this. So SID and SOD, serial data transfer, and here ALE, address latch control. Trap is an interrupt. Okay, so regarding this signal, I have not explained. Now, no need to answer this, but I'll explain you. Ready signal is in the microprocessor. Ready signal is used for communicating with the slower peripherals. Suppose here I am delivering at 2x speed, but you are not able to understand that. Suppose I am giving you at 200 kbps speed some data, but at the receiving end I'm able to receive at 100 kbps only. What happens? Half of the data is lost. So in that case, what happens is to avoid that problem, ready signal will be used. Once I send this data, when the other device is not ready, it will send the signal ready. Then only the next data will be transferred. This ready signal is used to communicate with slower peripherals. When the other device is not ready, the computer will enter into wait state. So ready will give you wait state. So first is 3 and second is 1, third is 2. 3, 1, 2. And the last one is 5. 3, 1, 2, 5. 3, 1, 2, 5. So which of the following interrupts is both level and edge sensitive? We have already discussed this. What is that? A trap. Consider the following features of 8085. So here in 8085 generally to connect any memory, we use 16 bits of address. But to connect any memory, connect IO, we might use 8 bits, that is called IO mapped IO, or sometimes we connect 16 bits, we call memory mapped IO. Now see here, in IO devices have 16-bit addresses. Originally IO device will be having 8 bits only. There can be maximum because 8 bits are used. See here, in memory mapped IO, I will tell you, listen here. There are two types of IO connections called as memory mapped IO mapped IO. That is to connect IO device to the computer. If IO device and memory device are treated in the same way, it is called memory mapped IO. If IO device and memory device are treated in a different way, then it is called as IO mapped IO. In memory mapped IO, we use 16 bits for memory and we will use 16 bits for IO also. In IO mapped IO, we use 16 bits for memory, 8 bits for IO device. In IO mapped IO, we use 250, 2 power 8 means 256 input devices and 256 output devices can be connected. But in memory mapped IO, total 2 power 16, 64 KB memory is used for both IO devices and memory devices. Now the question here is, memory mapped IO devices have 16-bit address, correct. IO devices are used with in and out. No, we use all the memory transfer instructions. There can be maximum 256, wrong. All the arithmetic logic operations can be performed directly on IO because they are treated as memory only. So 1 and 4 is the right answer. So which of the following is correct statement? Bus is a group of wires carrying the information, correct. Why buses are used? Because instead of connecting one device to another device, for suppose you want to go from one place to another place, one city to another city. There are thousands of people goes every single day. We don't make 1,000 different routes now. Common route will be used for all of them so that we can save. Definitely here the bus is needed to achieve reasonable speed of operation. Okay, bus can be shared by more than one device. The same group of lines, one device at a time we will use. But what happens is the other device must be deactivated. One device to be activated at a time. Bus can carry data or address, right? Here all of them are right. See, when you perform opcode fetch operations, there are some status lines which indicates opcode fetch is performed or read operation is performed or write operation is performed. Those are with the help of S1, S0 signals. When they are 1, 1, it is indicating opcode fetch. They are 0, 1, write operation, 1, 0, read operation. Here I am explaining the concept also with the help of problem to recollect you the content. And here IO by M bar signal is used. If it is 1, it indicate IO operation, input output devices operation. If it is 0, it is a memory operation. So how do you remember this? 1, 1 is opcode fetch, remember. How to remember 0, 1, 1, 0 means generally to remember easily, one trick is first we write, then only we can read. So 0, 1 and 1, 0 are assigned like that. So here what are the status signals for opcode fetch is the question. So S1, S0 must be 1. It is a read operation and ALE must be 1 in the first clock pulse because address latch enable is always given in the first clock pulse of any machine cycle. During the direct memory access, the interrupt and interrupt acknowledgement lines. See, we don't use interrupt and interrupt acknowledge for DMA. DMA is what? Direct memory access. Which lines are used during the direct memory access lines? Hold and hold acknowledge. So for DMA, what are the lines used is the question. What are the lines used? Hold and hold acknowledge. Interrupt and interrupt acknowledge lines are used for which operation? Interrupt operations. So what is the purpose of the DMA facility in the microprocessor? Why we use DMA? I already told you direct memory access is used to improve the speed. So to improve the reliability, no. To increase the speed of data transfer between the memory and IO devices, to increase the speed of data transfer between microprocessor and memory, no, microprocessor should not be involved here. To increase the speed of data transfer between memory and IO device, no. Between two different devices, maybe memory and IO device, between two devices, when you need to transfer the data, then we will use this concept, right? That is about the DMA. So in microprocessor with memory mapped IO, the devices have 8-bit address. No, I told you now, memory mapped IO requires 16 bits. The devices are accessed with in and out. No, maximum 256. Wrong. All arithmetic operations are performed with IO data, right? Because here memory and IO are treated in the same way. The remaining questions are based on what we call, we have a few more questions that those are based on what we call instruction set. So I can say, I can conclude this as a first part. In the second part, I will be discussing what we call the instruction set of 8085 and some basics of 8086, some basics of what we call 8051 microcontroller, and we will do some questions based on the instruction set of 8085. Okay. Hey everyone. So in the last session, we have a great discussion on the basic architecture of 8085 and the interrupt structure of 8085, the serial communication, all these basic things are covered in the first part. So in this part, we will be covering the instruction set of 8085. So this is one of the important part where we get more number of questions in every single examination, that is the instruction set of 8085. So here we will be discussing all the different type of instruction sets. But before going for that, instruction set of 8085 classified based on size. What is that size? Based on how much memory it require. We can classify 8085 processors into three types. 1 byte, 2 byte and 3 byte. The same way, the based on addressing mode we can classify into 5 types. Register addressing mode, direct addressing mode, indirect, like which we have discussed in the previous section. Other than this, based on function, means which particular job the instruction is going to do. Based on that, we can classify into 5 different types. The first one is data transfer group of instructions. The second one is arithmetic group of instructions. The next one, logical group of instructions. Then branch transfer group of instructions and machine control group of instructions. We will see all of them one by one. In a quick revision, let me quickly revive all of them. Like in a regular, if it is a comprehensive course, where we will discuss each and every instruction, how hardware point of view it will be connected, each instruction requires how much time, every single minute detail we will discuss there. But here we don't discuss all those things. Simply, what is the meaning of each instruction? Quickly we will try to remember, and any specific important point is there in that particular instruction, we might be able to discuss that. Then we will move for the new instructions. Then we will go to the problems. So at the end of the session, we will do all the questions. So here in 8085, we have 8-bit processor. So it can have 8-bit instructions register is there. 2 to the power of 8 different combinations it make 256. But out of the 256, they have used 246 different instructions. They have used only 246, remaining they have not used, they have not explained in the instruction set specified. In that 246 also, we have 74 something around different type of instructions. For example, there is an instruction move A comma B. Move B comma C is there, move C comma D, all under comes under only one type of, like that 74, 76 different type of instructions we are having. So total 246 instructions approximately, in that can be classified into some 76 different type of instructions. Now let's start with the data transfer group of instruction. In the data transfer group of instruction, the first instruction is move R1 comma R2. If you see this instruction, directly by seeing the instruction, you can say size of the instruction. How can you say size of the instruction directly by seeing, sir? Here no explicit data is there na. Explicitly outside this instruction no data is there, only opcode 1 byte instruction. Here 8-bit data and opcode 2 byte instruction. Okay, so what does it do? It will copy the register R2 will be copied into the register R1. Here the what about the register R1? It can be any register of A, B, C, D, E, B, C, D, E, H, L. Similarly, the register R2 can also be any of A, B, C, D. So total 49 different combinations are possible. Even move A comma A is also available. So total 49 different instructions are available here. Move R1 comma R2. Okay, like in the 246 already 49 are gone with a single code. So what it will do, copy the content of R2 into R1. It will not destroy R2, it will keep it as it is. The next instruction is move immediately. Example, MVI A comma 45. This number is immediately copied into accumulator. 45 means hexadecimal. Each digit is 4-bit, total 8 bits. Move R comma M. Here, whenever M comes, it is nothing but memory pointer. Okay. For understanding purpose, for example, H and L is having 3000, just for understanding. In 3000 location, some number 40 is there. If I say move A comma M, what the computer will do? Copy accumulator with the content of memory pointed by the HL register pair. What is HL register pair? 3000. 3000 memory location it will go, and if I keep this bracket, what is the meaning? In that location, whatever the data is there, 40 will be copied to accumulator. So that is the meaning of the memory pointer. That HL register will be having the address. In that address, some data will be there, copy to the register specified. Here, any instruction contains first part is opcode fetch to read the what we call machine code. Here, opcode fetch is only available. In this case, I need to read 45, na? This is called memory read. Here also I need to read 40, na? Memory read. So this instruction requires how much time, how many machine cycles is opcode fetch only. Here opcode fetch and memory read also. Here opcode fetch, memory read. So opcode fetch is 4T state, memory read is 3T state. How much time is required here is 7. But how much time is required here is only 4 T states. So generally while writing the program, we should count the number of T states to decide which program is more efficient. To do a particular job, two different programs are there. Whichever requires less time, less memory, that is more efficient. Here, this is a 2-byte instruction, this is a 1-byte instruction, this is a 1-byte instruction. Next, move M comma R means it is just reverse job of previous case. From the memory, earlier what we have done, from memory we have taken and copied to register. Now from register we will give to the memory which is specified with the HL register pair. Next instruction is LDA. You see here, this is 1 byte. This 16 bit means 2 byte. Total how many bits? How many bytes? It is a 3-byte instruction. LDA means load accumulator directly. What is the addressing mode? Here is direct addressing mode. Here memory pointer is used means register indirect addressing mode. Here immediate data is specified in the instruction, then it is called immediate addressing mode. Here data transfer between register to register, it is a register addressing mode. So generally this memory data transfer will happen register to register, register to memory, memory to register. In 8085, direct memory to memory instruction is not available. So come here, what it will do? For example, if I say LDA 3000, suppose in the memory location 3000, some 45 is there. Then accumulator will be copied with the content of the memory location 3000, that is 45. So in the instruction, whichever address you give, computer will go to that address, copy it. So here in computer 8085 is called little endian processor. What is the meaning of that? I will tell you. How do you save this is like this. Load is having some machine code. Then 3000, first we store lower byte, then we store higher. Lower byte is stored first, then it is called little endian processor. Then at 3000, we have some 45 now. So first it will do opcode fetch. Go here, read it, then save it in some WZ registers. Then come to that 3000 location and read this data and give it to accumulator. So how many machine cycles are involved here? 1, 2, 3, 4. Total time is 4T plus 3T plus 3T plus 3T. 13 T states time is required to perform this operation with the 3 bytes direct addressing mode. The reverse job of this is store. There what happens? For example, accumulator is having 25. If I say store accumulator into 3000, so it will go to here 3000. In 3000, whatever we have, it will replace with the new accumulator value. That is, content of accumulator is copied to memory 3000. So it is same process, but last job is not memory read. Lastly, it opcode fetch it will do as it is for store accumulator instruction also, but instead of memory read operation, lastly it will do memory write operation. So that is about load and store. Load means it will copy accumulator, copy to accumulator. Store means accumulator to memory. Similarly, load indirectly, instead of giving the address directly, here it is indirect addressing mode, where we can say LDAXB. Then what happens is BC register pair will be having the address. We will go that address and copy it to the accumulator. So here In the instruction, we don't specify the address, na? So 2 bytes are saved, only 1 byte is enough. But my BC register must already have that address. In that case, it will help you. Okay. Then accumulator will go to that location. For example, BC equal to 2000. Then 2000 we will go, and whatever we have here, it will read and give it to accumulator. So here first it will do opcode fetch, then it will understand this is the job, then it will read BC, BC address will be taken and read it here. In the previous instruction, we need to read address in the instruction itself, then 2 extra cycles are required, but here only opcode fetch and 1 memory read is sufficient. So how much time is required here is for this 4 T states, 3 T states, 7 T states. It's a 1 byte instruction only, because in the instruction we are not specifying the data. Its reverse is a store. Accumulator is given to the register pair address. Address is specified in the register pair. We'll go to that memory and write it there. The next one is load register. Suppose here I told LDX BC should have this 2000. That can be done with the help of this instruction. Load immediately. You can take any register pair, HL, BC, DE, stack pointer also with 4500. Then HL will be copied with the number you have given. Here you have LDX BC or DE, not HL, because LDX HL is equal to another instruction, move A comma M is there. 1 minute. Here the last instruction is exchange. What happens is the content of HL register pair will be copied or exchanged with DE register pair. This is what we call exchange instruction. The next one is move M with the immediate data. So what is, whenever M comes, what is the meaning of that? HL register pair. So HL might be having some 3000. Okay. Then if I say, for example, move M comma 44. This is opcode. Some number is given. Computer will read this. Then it will understand to read the next byte and write that data where? In 3000 location. Next one is load HL pair directly with 16-bit address. This instruction, what happens is, for example, if I say LHLD 3000. See, this is little lengthy time processor. It will do opcode fetch, memory read, then it will go to 3000 and 3001. In these two locations, some numbers are there, na? Those numbers, it will copy to HL register pair. So its reverse job is SHLD, where H and L will be given to, like L is given to this location, H will be given to this location, then it is called store HL directly. What it is doing is, it will read the address in 2 next locations. HL pair will be, those 2 data will be given to H and L locations. First will be given to L, next will be given to H. Okay, here 1, 2, 3, 4. How many machine cycles? 5. 4T, 3T, 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 3T. Total 12 plus 4, 16 T states time is required to do this job. So its reverse is store HL pair directly. So this finishes the data transfer group of instruction. Now, because for data transfer I have explained elaborately. Why? Because to understand the concept and each internal thing also. For example, here what is the addressing mode? Directly address is specified, direct addressing mode. Here immediate addressing mode, but M is specified. Whenever M comes, a register pair is used indirectly. All these indirect addressing mode. Here it is immediate addressing mode. Here implicit addressing mode, because no specific data is specified. Indirectly storing, this is a register indirect addressing mode. Right. Now let's go to the next one, what we call arithmetic group. In arithmetic group, 8085 have addition, subtraction, no multiplication and division directly available. Increment, decrement are available. If you see addition instruction, we have the variance block add or add immediately 8 bit, add with the carry or add immediately 8 bit with the carry. So here add instruction, add or means, for example, you have add B. It will add A with A plus B. It is a single byte instruction. It requires 4 T states, only opcode fetch, no memory read operations and all. Register addressing mode. In all add operations or subtract operations, directly the result is stored in accumulator, and one of the operand, because to perform addition we have two operands, one of the operand is always accumulator. You can see by default if I say add B, B is added to whom? A only. Add immediately 8 bit now. In this it is like add EI 24, then accumulator is added with EA plus 24. Add with the carry means what happens is, if I say ADCB, accumulator is added with A plus B plus the carry from the previous addition. From the carry from the previous addition. Same add carry immediately 8 bit data. So these two are 7 bit, what we call 2 byte instructions. These two are 1 byte instructions. These are register addressing mode. Second and last are what we call immediate addressing modes. Similar to addition, we have subtraction also. So there is add instruction, add or sub or, add immediately, subtract immediately, add with carry, subtract with borrow. But in 8085, how subtraction is performed is internally with the help of 2's complement arithmetic. After the addition or subtraction, all the flags will be affected. In the data transfer group, no flags will be affected. After the addition and subtraction, all the flags will be affected. So while these flags are getting affected, how they will be affected is based on the result. But after the subtraction, carry flag will be complemented to represent borrow. I'll explain this. For example, move immediately A comma 40. Subtract, sorry, A9. Okay. A comma 40. Move immediately B comma 50. Subtract B if I say. Suppose if you subtract 40 minus 50, what is your answer? Minus 10. Minus 10. So the answer is negative. Okay. I cannot take 5 from 4 now. We need to take a borrow to perform this operation. So this is where you need to require a borrow. How computer will do this internally is, listen here. I will show you. Accumulator is copied with 40. 40 in the hexadecimal is 0100 B is copied with 50. Okay, so when I say subtract B, then 01000000 will get added to 2's complement of this. What is 2's complement of this? All zeros, right? What is this 2's complement? 1111, sorry, 1010, all ones. If you add 1 to this, you will get this answer. This is the 2's complement. 1 minute. Correct. Now, if you add them, this is the result. Okay. No carry is generated. But what is the carry flag after subtraction is complement of original carry to indicate borrow. This happens in the internal of computer. What is the parity flag here? Even 1. What is the 0 flag? 0. What is the sign flag? MSB of the result. When sign flag is 1, the result is negative. For example, same question, MVI A comma 40H, MVI B comma 30H, subtract B. See, if there is a borrow from here to here, that is what we call auxiliary carry, auxiliary borrow. Now what happens? 40 is how much? 0100, 0000. 30 is 00110000. So what is its 2 complement? 11010000. So add them, 1 0 1 plus 1 sum 0 1 plus 1 sum 0 carry 1. Here this is your result, which is 1 0. 40 minus 30 is 10. Here what is your borrow flag is complement of this. It means there is no borrow. Always after subtraction, computer internally do the complement of the original carry generated to indicate borrow. Here reminding, what is the sign flag here? 0 to indicate the result is positive. 0 flag is 0 because the result is not 0. Like that, all flags will be affected after addition and subtraction. Similar to addition and subtraction, we have increment, increment register pair, decrement, decrement register pair. Increment can be done for a register, decrement can be run for a register pair. This is a cyclic increment. For example, 0 is incremented 1 up to FF. After FF, if I increment, it will go to 0. In increment and decrement, all flags will be affected except carry flag. For INX, DCX, because it is a 16-bit incrementation or decrementation, no flags are affected. Because my flag register is based on ALU, which is 8-bit operation only, it can track. So INX, DCX are incrementing the register pair. For example, here you have a number 27FF. If I add 1 here, what happens? It will become 2800. But if I add 1 only for FF, then it will become 00. Then 27 is not incremented, only 0, this part is incremented, it is a 8-bit incrementation. If you add total number is incremented, then it is called 16-bit. So INX and DCX will do this. So here we can also increment memory also. That is the content with the HL register pair. Increment memory is available. That is the content of the memory location pointed by the HL register pair. It will take it, increment and write it back. Add with register, add immediately, add memory is also available. Now, similar to add and decrement, we have one more thing called DAD. DAD means double addition. When you do 16-bit operation, this double addition will help you. So double addition RP means register pair will add. HL is added with HL plus the given register pair. This is the instruction where we require 10 T states, 4 T states for opcode fetch. Because it is a longer operation, we require 2 more states called 2 bus idle. It will not do memory read, memory write, but computer will take some time to perform this operation. That is what we call bus idle. So the next, logical operations. There is one more instruction also called DAA, decimal adjust accumulator, which is used to adjust the result into BCD format after normal addition is completed. Logical operations we have AND, OR, XOR. Generally, AND operation is used for masking. OR operation is used to set a particular bit. XOR operation can be used to complement a particular bit. Suppose, because if you XOR any bit with 1, you will get a complement of that. If you what we call OR any bit with 1, then what you get in the particular answer will be 1. And similarly, if you AND any bit with 0, you will get 0. So these logical operations the computer can do. It can also do rotate operations, and can also do compare operations. All these are the logical operations performed by the 8085. In end, we have the operation ANA, AND R, AND with the register, AND with the memory, and immediately with the data. The same we have with OR operation and XOR operation also. If you XOR A with A, you will get 0. It is used to clear the register with least possible T states. Rotate instruction, we have two types. Rotate means nothing but shift, but last bit will go to first bit will go to last. The remaining bits will be rotated like this. This is rotate left. There is another case called rotate left without carry, means 8 bits will be rotated. Here carry and accumulator together 9 bits will be rotated, then rotate accumulator left. In rotate left without carry, this is the process. This MSB will go to carry and the MSB will go to the last bit also. This is a 8 bit rotation, this is a 9 bit. In rotate we can also have rotate right also. The last option is compare operation. When comparing the two, accumulator is, suppose you are comparing a register and accumulator. Accumulator is greater than register, accumulator is less than a register, or accumulator is equal to a register is specified by this instruction. If accumulator is greater, then 0 flag is 0, sign flag is 0. When accumulator is less, 0 flag is 0, sign flag is 1. When accumulator is equal to register, 0 flag is 1, sign flag is 0. This is 0 flag is 1 means both are equal. How compare operation is performed is internally by subtraction, but that result is not stored anywhere. Here you can see the flag registers will say whether A is greater than R or less than R or equal to R. You can compare immediate data. You can also compare any memory also. So those are the logical instructions of 8085. Flags will be affected accordingly. But in these operations, carry and auxiliary carry are having fixed values. So the next group of instructions are branch control. Those are jump, conditional and unconditional, jump on carry, jump if no carry, jump on parity, jump on positive, negative, parity, even, parity, odd, jump on 0, jump if no 0. What is the jump instruction means? Suppose jump 16-bit address. If I use jump 16-bit address, what happens is all of a sudden, if the program is running here, want to move to the new location, I'm sorry, then jump instruction can be used. Then the program will go to the new location completely. So this is a to move to the new location, it is a 10 T state instruction. 3 bytes and 10 T states time is required. But jump to be happen only based on some condition, then it is called a jump on carry, jump on no carry, jump on parity. Based on the flags, this will do the jump. These are used in the loops. When 0 is set, jump, otherwise continue, like that. Similar to jump, there is another instruction called call. But in the call instruction is the lengthiest instruction, longest time it requires. In jump instruction, CPU will not save the current location. So CPU cannot come back to the new location. Once it jumps from there, it cannot come back. But for call instruction, the CPU can come back. Call is followed by return. Call and return also unconditional, conditional. What happens in the return is it will come back to the wherever it has left, it will go back. Suppose I am CPU is doing some program. Suddenly call instruction comes. From this location it will go to new location. After when return happens, it will go back to the original location. How computer knows the original location again, sir? It is save that location in a memory called as a stack. There are another instructions called SPHL, PCHL, RSTN. RSTN is a what we call like a 1 byte instruction only, but it is a software interrupt. Whenever RST happens, computer will jump to the location of n into 8. PCHL means program counter is copied with the HL register pair. Here it requires 6 T states for opcode fetch. Similarly, INX DCX also requires 6 T states in the opcode fetch. Call instruction also, because whenever push is there, it requires more time because of the pre-decrement operation. So the next is a stack operations. In stack, let me explain you push operation. In 8085, how push operation happens. The stack pointer is pointing to some location. Whenever push operation happens, suppose if I say push a particular register pair, first step is decrement the register stack pointer. First step is what? Decrement the stack pointer. It is called pre-decrement. First decrement, then write that register pair high. Then again, this is the second step. Third step is again decrement, then write the lower byte. This is what happens when you do the push operation. So you can push any two registers, PC, accumulator and flag register is togetherly called as program status word that can be pushed. Push B means B and C will be copied. Push D means D and E. First here decrement is to be done before writing. That's why stack opcode fetch requires more time, 6 T states, and to memory writes we are doing another 6 T states, total 12 T states time. Another one is called pop RP. See, for example, already the computer has done this job. Now it is here. Previously we have done push. So I am here. For understanding purpose, let me here. This push is B and BC is containing 40, 50 numbers. So what I will write is here. BC is containing, first I will write B here, C will be copied. Suppose if I say pop D, then the first what it will do is, it will first step will be memory read. It will read to E or your register pair lower part. After that, second step is increment the stack pointer. So stack pointer will now come to this location. Third step is again read that value to the D register. Fourth step is increment stack. So it will come back to its original location. So pop push operation will decrement the stack by 2. Pop operation will increment the stack by 2 in 8085. Push is a pre-decrement, pop is a post-increment. First it will copy it, then it will do increment. That's why its opcode fetch requires 40 states only, and it requires less time to do this operation compared to this. Here it requires 12 T states, here it requires only 10 T states to do the job. So after this, what happens is, in whatever you have in the BC will come to DE, right? So like that, about push and pop operations. So there are two more instructions in this. Exchange the top of the stack with the HL register pair. So HL register pair and the top two locations of the stack will be exchanged, and SPHL is there where stack pointer is copied with the HL register pair. I'm sorry. So the next is, there are two IO operations, in and out. Here the IO address data will be copied into accumulator. There is some input device at that address, some input device is there. Whatever the data is present in the input device is given to accumulator, or from the accumulator we give it to the output device. For that we use in and out instructions. These are used in IO mapped IO configuration. So the last one is machine control. In the machine control, we have enable interrupt to enable the interrupts, disable interrupts to disable all the maskable interrupt, set interrupt mask, read interrupt mask, halt. Halt will end the program. So this is the interrupt structure of 8085. You can see 7.5, 6.5, 5.5 interrupts can be masked. But a trap interrupt, if you see, there is no possibility of masking the trap interrupt. A trap interrupt is direct. But 7.5, 6.5, 5.5 can be masked with this. If you keep here, one bar will give you 0 and the output will become 0. This is what happens here. So whenever a disable interrupt is 1, then you will get 1. This will be reset and this will clear all the AND gates. Whenever disable interrupt is 1, all the interrupts will be disabled. When any interrupt is recognized, nested interrupt means one interrupt is acknowledged, in between another interrupt cannot come and disturb in 8085 except for trap, which is a special case. Here all are level triggered. Level triggered means it should happen, it should be 1 and it should wait until interrupt is recognized. But for 7.5, it is edge triggered. What is the meaning of edge triggered? Whenever if I give the interrupt request to the here, once the edge happens, the flip-flop will copy it, and even that trigger is removed also, the flip-flop will save it until the request is completed. Once request is completed, then it will clear it. But you can clear it with the help of another reset 7.5 pin, that is directly we can clear it. What is the meaning of it? I'll explain you. What is the difference between level and edge triggered interrupt? Suppose you went to a bank, there is a big queue. You are in the queue until your job is completed. This is called level triggered. In between, if you go back, your position is gone. But in the queue, you know some person. You went to bank, you have given a form to the person who you know it, and you went away, but your work will be done. This is what we call edge triggered. So your interrupt has occurred. At that time, computer is busy, no problem. We will save that interrupt in the D flip-flop. Once the computer is free, this D flip-flop will take care of running that interrupt. So to set the interrupts, there is one instruction called SIM, set interrupt mask. Here we keep the required bit pattern in the accumulator and we use the instruction SIM. Then what happens is this bit is used for serial output data, this bit is used for serial data enabling, and this bit is unused, it can be any value. It is used to reset the 7.5, suppose 7.5 request raised, it is waiting here. If I want to reset it without accepting it, then I can use this bit. This is to enable the mask set enable, to enable the maskable interrupts. If you want to mask any of the interrupt, what is the meaning of masking? Even that interrupt occurs also, if I mask it, it will not read. The AND gate will become 0 only. For example, if I want to mask 6.5, then I keep 1 here and 0 here. Now what is this value? 1101 is D. The 1010 is A. What I need to do is keep this value in the accumulator and say SIM. Enough. If you say SIM, it will do this job. What it will do? Serial output data, it will give 1. Serial data will be enabled. It will reset 7.5. Mask set is enabled and 6.5 will be masked. This is how you set interrupts. There is another option called read interrupts. That is, any interrupt is pending, any interrupt is masked. All these can be read with the help of read interrupt mask instruction. After rim instruction, the required data will come into accumulator, which we can analyze it. So first bit will tell you serial input data. The second bit, these three bits will tell you which interrupt is pending. For example, 010 comes, it says that 6.5 has occurred, sir, but it is pending, not serviced. So the time between occurring of the interrupt and actual occurring and actual service, once the interrupt has occurred, when it is getting the service, or there will be some process in between, what we call interrupt is acknowledged, and the current CPU is doing some program, it will save its program counter in a stack and it will send the acceptance. This gap is called interrupt latency. Latency is means the delay between actual occurrence of the interrupt and actual response of the interrupt. The next one is interrupt enable flip-flop. All interrupts are enabled or disabled. This will tell you which interrupt is in masked condition. Suppose any interrupt is masked, suppose 7.5 is masked, it will give you 1. Suppose if you got the data like this, after RIM if you got some data like this, what is the meaning of that? Sir, you got a data like EAD, AE. What is the meaning of that? Serial input data is 1, 6.5 is pending, and 7.5, 6.5 are in mask condition. Interrupt enable flip-flop is 1. When interrupt enable flip-flop is 0, what happens? Interrupt enable flip-flop is 0, all interrupts will be disabled. You can see here, EA and DA. So this is the flip-flop. When EA is the interrupt enable instruction 1, then it will enable all. When disable interrupt instruction is 1, it will disable all. Or when reset of the system occurs, it will disable all the interrupts. When any interrupt is accepted, then also it will disable all the interrupts. These are the three cases where this interrupt enable flip-flop will be disabled. Which interrupts it will disable? Only maskable interrupts. This is a non-vectored interrupt. Its address is not fixed. Address will come from the device which is interrupting this. But all these interrupts will be disabled when this interrupt enable flip-flop is 0, except a trap. So that is about your interrupts. Now, if you come to 16-bit processors, 8086 is a 16-bit processor. Compared to 8-bit, they will be having more processing capabilities, advanced architecture, and more memory, more data handling capabilities, and more better instruction set. This is a 16-bit processor. First part is the bus interface unit, and another one is the execution unit. And here these are the registers AX, BX, CX, and DX, stack pointer, base pointer, source index, destination index. I'm not going to much deeper here because this is a completely different subject. Just overview I want to give you. So in 8086, instruction will be kept in a 6-bit queue, 6-byte queue. So one by one it will load. Once it is out, another byte will be loaded like this. So this part will do the execution part. This part will take care of taking the data from the external. So data is segmented memory is used here. So memory is accessed with two people. One is segment register and offset register. Each segment parts it has made, in each part where it is given by the offset. So features, you can see 16-bit processor, 20-bit address line, so 2 power 20, 1 MB memory capability, 16-bit address lines, and clock frequency approximately 5 MHz. So it can do 16-bit operations, and it has an operation of multiplication division also. So it has an operation mode of single processor and double processor also. It has like hardware interrupts, we have five there, here 256. And more powerful compared to 8085. Maximum mode, minimum mode it is there, and it will also accept string operations. A group of bytes can be transferred at the same time by setting a counter on its own. Direct string operation instructions are available. So that is about your 8085 processors. It has multi-programming mode also. In 8051 is a microcontroller. In microprocessor, external interfacing devices are externally available. No extra memory is available, but all of them are inbuilt in microcontroller. In microcontroller, there is a 4 KB on-chip program memory, 128 bytes of data RAM, because these are the questions they can come immediately in the exam, right? It is a 8-bit CPU, 64K programmable address space. It is not in the processor, but it is having that capability. Data memory space, 32-bit bidirectional address IO lines, and it has two 16-bit timers, full duplex universal receiver transmitter, asynchronous UART, and 6 or 5 vectored interrupt structures with 2 priority levels. On-chip clock oscillator also. So all these are the features of 8051. memory they will ask you. Okay, please remember 4 KB on chip program memory and 128 bytes of RAM. So let's now, that is about your theory. Now let's have a discussion on the problems based on what we discussed till now. Already few questions we have done on the previous session. Now see here. Consider the following statement. Whenever reset instruction is executed, generally in 8085 when reset instruction is executed, program counter will become 0. All interrupts will be disabled. I told na, and reset out pin will be logic 1 because reset is happened to indicate that. So first only correct. Right. Let's start. Read one by one. We will discuss all the questions. In 8085, after the execution of XOR A, when you do A XOR with A, what is the answer you get? 0, na? So when it is 0, 0 flag will be equal to 1. Simple. Next. Consider the instructions of 8085. Move M comma A, add C, MEA, FF. So which of the following can change the status of the flag? I told you, na? Data transfer group instructions cannot change the status. Arithmetic and logical group of instructions can change the status. So 2 and 4. So so a little lengthier question is given. Consider the block of program to transfer the data of 5 bits from A000 to 9000. From this location to this location, I want to transfer 5 bits, 5 bytes of data. So 8000 to 9000, A1001 to A0001 to 9001, like that 4 bytes. So first what he has done is the program is like that, copied the initial addresses here. Okay, he has copied the counter value here, then move A comma M. So accumulator will be copied with the content of memory location pointed by HL register pair, that is A00. Okay. Now I need to copy this to what? 9000. Then store accumulator to B. So B will be copied with the content of accumulator, that is content of A00. Okay, no problem. So firstly, then what is B? 9000. So this is 9000. So first it has done properly. 8000 to A, then A to 9000 it has copied. Then increment B. So B will be 9001 decrement C. Okay. B is incremented, decrement C. C will become, counter will become 4. Jump if no 0. It is not 0 na, it will go back and do this job. It will go to 3, 2, 1, 0. It will stop. But this program is not working. Why it is not working, sir? Because very simple rule. You can observe. He is incrementing B but not incrementing H. Why H is to be incremented? Because you understand, first byte is copied in 8000, 9000. Next byte is to be copied from 8001 to 9001. So here incrementing only B, na? He is not incrementing C. So what is that? C register is used as a counter, no? Okay, that is also problem. Listen. Increment B means what happens here? BC register pair is getting incremented. Decrement C means C is again decremented. Here C becomes 0, 1. Here C becomes 0, 0. Then what is the use of it? You understand what I am saying? Here he is incrementing BC, and here the same C is used for the counting operation also. He should not use the same register in both the places. So that is correct. In decrement C instruction, this is the correct answer. In fact, there is one more problem with this is he should increment what we call HL also, H also, that is also missing. Next question. With the reference to the 8085 processor, which of the following statements are correct? Add instruction adds the content of specified register to DA. No, I told you to HL register pair. Program counter is a instruction pointer. Yes, it will point to the instruction pointer in 8086 is the program counter in 8085. Whenever an instruction uses HL register pair, the addressing is indirect. Very good. Because HL is what? HL is called memory pointer. HL is called memory pointer. HL is called memory pointer. So the point is right answer here. Next. HL register pair is also called as a data pointer. That is also correct. So what are the right options here? 2, 3, 4. Next. On 8085, which of the following machine cycles are not used for call instruction? Opcode fetch is used, memory read, memory write will be used, IO operation is not used. Okay. During call, what happens? It will opcode fetch, then it will write its program counter value into stack. So memory write, then it will go to the new location. Okay, because stack will be updated. So first what happens is the call instruction, opcode fetch, then it will understand, it will also read the address where it will need to go. So memory read it will do, two memory reads, one opcode fetch, and it will write in stack two memory writes also. 5 machine cycles it will take, but no memory write is there, read is there, but no IO operation. Addressing mode, the addressing mode in which the location of the data is contained within the mnemonic is known as. So here what is that? The addressing mode, the location of the data is contained within the mnemonic is known as register addressing mode. No. Immediate location of the data is, here he should specify little clearly, but anyway, within the mnemonic itself the data is specified, generally we call it implied addressing mode. Or within the instruction itself, if immediately instruction data is available, then it is called immediate addressing mode. Which of the following type of instruction used to copy from source to destination? Data transfer group. Push and pop instructions are performed for which operation? Stack register. Got it? Because push and pop are for stack. Which of the following instructions uses implied addressing mode? I told already, complement accumulator. Because there jump you specify address, ADC with register, subtract with borrow, registers and all. But CMA, complement accumulator, there are instructions like set carry, rotate carry, complement carry, STC, CMC, complement carry, complement CMA, complement accumulator. All these directly happens on one specified operation, instruction only, one specified operand only. There is one instruction called NOP, no operation. It will not do any job. For how many T states is 4 T states. That is also there. Now let's try this question. Accumulator is copied with 45. You need to copy B with accumulator. STC means set carry. CMC means complement carry. Now see, rotate accumulator right. RAR means through carry we should do it. Rotate accumulator right through carry. Firstly, what is the value it is having accumulator? 45 na 0 1 0 0 1 0 1. And he said, what is the carry initially? 0. Now what I will do is simply rotate means all bits will be rotated. Last bit will come here. This bit will come here. So just keep this here. Strike it off and keep it here. Now this will be how much? 20. Now XOR A with B, that is my accumulator is 22. What is the B register contains? 45. Dono XOR please, both of them 1 1 1 0 0 1 1 0. So this will be 67. What is the content of accumulator after this program is 67. You understand rotate operation? Na? Last bit will go to carry. This bit carry will come to the first bit because it is rotating right through carry. RAL means rotate left through carry. RLC means rotate left without carry. RRC rotate right without carry. I tried all programs such that each question will cover some concept. It will give you like a good quick revision. So stack pointer here is 27FF. Okay. If I say call, after call instruction, what happens? I told because call, it will save the content of the program counter and go to the new location. So where it is saving the content of the program counter? In the stack. So stack pointer will be reduced by 2. Then pop operation, push will reduce by 2, pop will increment stack pointer by 2. Okay. So what are the contents of the stack pointer HL register pair after the execution? So stack pointer will be 27FF only. Why? Because it will not change. Now, what about HL register pair? See here. Your program is at 1000. At 1000, I have written SP FF 27. Next, 1003, I have written call 0610. After call, now it will do pop, but pop is at where? 1006. Okay, pop is only 1 byte instruction. Now see here. What about the stack pointer? Firstly, stack pointer is at 27FF. Okay, here it will do push operation because the call will do push operation. So during call, it will decrement the location 27FA and write the higher byte of the next location of the call instruction. What is 104? 6 is the next location. So it will store here 1006. It will shift decrement. Right. Now, when I say pop here, pop means pop to what? HL. HL is copied with the these two. So this will go to L and this will go to H and it will come back to its own location. So HL will contain what? 1006. So when I say pop, it will copy pop with. So this is the final answer. Whatever call instruction pushes, when you say pop, it will take back those locations to the specified register pair HL. So HL contains 1006, SB contains 27FF. So small code of 8085 is given below. Okay. Accumulator contains 7F. What is 7F, sir? 0, 1, 1, 1, 1, 1, 1, 1. Or A with A. So or A with A will give you again same or not, because A plus A or with A bitwise is give you A only. If I do OR operation of same, 0 OR with 0 is 0, 1 OR with 1 is 1. It is not addition, OR operation. Right. Compare immediately with A2. 7F is less than A2. Then what happens? My sign flag will be 1. 0 flag will be 0. So what about the sign flag here? 1, sir. 0 flag will be 0. No carry flag. Okay, here carry will not be generated. Firstly, what about accumulator? Accumulator will be copied with 7F. Because OR A with A will not, A, if you OR with A, it will give you A only. Compare operation will not disturb A, it will only compare and affect the flags. So this is the right answer. After the OR operation, okay, This is the result. Let me go through the next question. Okay. Just a moment. Next question. Right. Okay. So one more thing, generally for OR operation, carry flag will become 0. But while comparing, how it will do the comparison? It will do by subtraction. When you do subtraction of A2 minus 7, if you need a borrow, that borrow is indicated by carry here. But that result will not be stored anywhere. That's why carry has 1 here. Whenever A less than B happen, that is when accumulator is less than the comparing value, then sign flag will be 1 or carry flag will also be 1. So this is the answer. Next. Consider the following loop XR A. Okay. Accumulator is cleared here. It is used to clear accumulator with lowest number of T states XR A with A. Because if I say MVI A comma 0 0, A will become 0, but 7 T states and 2 bytes. XR A with A will become 0 with 4 T states and 1 byte. So B will be copied with 0007. DCXB, so B is decremented to 0001. Jump if no 0 to loop means if it is not 0, go back to loop. It is going back to loop. It will become 5, 4, 3, 2, 1, 0, 0. But in this case, for 0, 0 also it will go back to loop. How many times it is going to loop means it is not 8, it is not 7, not 1. Because here it will repeat up to infinite number of times also. It will repeat up to infinite number, can repeat up to infinite number of times also if, because DCX, I told already, DCX will not affect the flags, INX will not affect the flags because it is a 16-bit operation performed outside the flag ALU or flag register capability. So here first instruction is there now, XR A with A, accumulator becomes 0 here. Here itself your 0 flag will be 1. So because of this 7 6 here, jump if no 0 to loop, it is saying it will not go back actually. So it will not go back. It will decrement to 6. But jump if no 0 means it will check flag only, not register. It will check flag only. That flag is not affected by this DCX instruction. Whatever flag it is having, 0 flag is 1 here because of this. So it will come out. So only one time it will do. Suppose if this is not there, it will do infinite number of times. But if you want to do it for 7 times only, you should use DCR here. DCR, not DCX. So 8086 is a 16-bit processor 40-pin IC. So the content of the accumulator 8085 is not altered after the 1 minute. Content of accumulator in 8085, yes, you can see here accumulator content will not be altered, or if you are with B it will change, move with A it will change, and it will change. If you do compare, it is actually not CIP, it is compare. After comparison, accumulator content will not change, only flag registers will be affected. Only flag register will be affected. If the last address size of 4K, this is a memory concept. 4K means, see here, 4K means 2 to the power of 12. Okay, you can see 2 to the power of 12 means you take 12 bits. What is this? Yeah, yeah. Now come here. So last is 3 triple F. Then what is the first? If last is suppose last is 0 double F, triple F, first is triple zero. So last is 3 triple F. What is the first one is 3 triple zero. Subtract this number from the this one, you will get the last address minus this size. This will give you the total. This value will tell you the first one. So if it is 16 KB, take 2 to the power of 14 like that. So subtract this triple F. Excuse me. FF means 255 in decimal. Decrement, it will become 254. Is it 0? No. Go back. 253, 252, 251, and so on. 8, 7, 6, 5, 4, 3, 2, 1, 0. Come out. So 254 to 0. How many times it is doing? It is doing 255 times. Right? So if you start with 0 na here, 0 decrement will give you 255 because it is a cyclic operation like a counter. In that case, it will do 256 times. Okay, so here it is 255 times. If you have doubt, don't do all. Just take small number 4, 3 and check how many times it is doing. For 4, it is doing 4 times. Then it is for 255, it will be 255 times. For 4, it is doing 5 times. Then for 255, it will be, what is that? 256 times. Like that, we can approximate also. If it starts with 0, 0 here, it will do first decrement, 0 decremented will give you FF, that is 255. And in that case, it can it will perform for 256 times. Next, 8085 assembly language instruction that stores the content of H and L registers into memory locations. So here, content of H and L registers are to be copied to these two locations. So what we need to do, SPHL or SPHL, XTHL, exchange the top of the stack, or SHLD. I told na, store HL pair directly. First address is specified, so two consecutive locations, it will copy H and L. Next two locations, first location L and next location H. So that is what I want to give you guys for this microprocessor in the shortest possible time. So for your exam, I hope within the least possible time, just quickly revise the things and enjoy your exam. So we have microprocessor, generally they will give questions in any exam, not only this, in any JEE exam, questions will come compulsory. I suggest you, wherever you give you more number of exams, prepare this subject exclusively. Here I just gave you in the 2-3 hours or whatever may be the time, very less amount of time, in the whatever possible I have given. If it is a full course, there we will be discussing each and every minute detail, like building the blocks, everything we will discuss, and you will enjoy the subject. Those who already studied can definitely understand everything here. But if you are very new, maybe up to some level, definitely it will help you for your examination if you at least attend these two parts. Okay. So all the very best. Thank you all. Bye bye. So after your exam, one more point I want to add. So after your exam, you can comment your what we call how you are able to make it your response, how this session helpful for you in the comment section of this video. Okay, thank you.